Once around Altair, one of my favorite stars in the summer sky. Altair is the brightest star in the constellation of Aquila the Eagle, 12th brightest of all the stars in the night sky, magnitude 0.7. And the name comes from the translation of the flying eagle. The rest of the stars in the constellation, not so bright, a little bit hard to find. We can always find Altair because it's one corner of the summer triangle, the other two being Vega and Deneb. And that was an asterism made up and popularized by Sir Patrick Moore and by H.A. Rey in the United States. Very useful for navigating your way around the sky in the summer. Now, Altair itself is one of the sun's near neighbors, and this is why it appears so bright. It's one of the brighter stars within 20 light years of the sun, at just 16.7 light years away from us. That puts it inside what's called the G cloud. That also contains the Alpha Centauri system, and the sun is heading that way. It will enter the G cloud from the local cloud that it's in at the moment. The local interstellar cloud, the LIC, is that yellow region with the sun in it. And in about 2,000 years' time, that we will leave the local cloud and enter the G cloud. The local cloud itself is actually moving laterally across the direction of the travel of the sun. So we're both moving, and the sun will exit in about 2,000 years' time. Now, the G cloud is a relatively low density. It's 1/3 of the density of material of the local cloud, and that works out to be 0.1 hydrogen atoms for every cubic centimeter. So you need 10 cubic centimeters to gather up one atom in the G cloud. That's pretty low, but it's 3 times higher than that in the local cloud. And we are traveling through that at the moment, and as I say, we will drop out of it at some point in about 2,000 years' time. The LIC and the G cloud are both part of a much larger structure, 1,000 light years across in the Orion arm of the Milky Way galaxy, and that's called the local bubble. And here the density is 10 times lower, 0.05 atoms per cubic centimeter. So in fact, the G cloud is 20 times the density, and the LIC, where the sun is now, 3 times more even than that. And this is quite an amazing structure. The average density around the whole of the Milky Way is about 10 times higher than this local bubble. So Altair itself is a main sequence star, an A-class star, hotter and bigger and more massive than the sun. The mass is worked out to be 1.86 times our own star, and a larger radius, and 11 times the power output. As you raise the mass of a star, it tends to raise the power output according to a rule which has a 2.5 power in it. So 1.86 to the power 2.5, if you can work that out for yourself. But the result is Altair is 11 times brighter than the sun. The spectrum shows a very strong peak in the blue end, the high energy end, corresponding to a high temperature, and those lovely absorption lines corresponding in the main to hydrogen in the atmosphere, in the outer layers of Altair, characteristic of a main sequence star. What's unusual about Altair is just how fast it spins. The sun takes 26 days to rotate on its axis, Altair just 8 hours. And the speed at the equator, 286 kilometers per second, that works out to be 67% of the breakup speed. So the centrifugal force, if you want to call it that, is 2/3 of the strength of gravity at the equator, and that is making it highly oblate. And the image on the right is actually a representation of real data from a number of different interferometers, and Altair is one of the few stars that we have been able to photograph the surface of. So 20% fatter across the across the equator than it is at the poles. And also the spin axis is tilted at 60 degrees to our line of sight. Now, that spin creates a phenomenon that is sometimes called gravity darkening. And we have a hypothetical star at the top here. It's perfectly spherical when it's not rotating, and as it speeds up, it becomes more and more oblate, more and more ellipsoidal. And the result of that is that the equatorial regions see a greater centrifugal effect, moving mass away from the spin axis, lowering the pressure in the gas, making it less dense and cooler, and the poles are hotter. And so, in fact, Altair has a temperature of 6,780 Kelvin at the equator surface, but a much hotter 8,620 at the poles, nearly 2,000 degrees hotter, just because of this gravity darkening. And in fact, a more mathematical treatment of it is called von Zeipel's theorem. And this takes into account the centrifugal effect of the rotation using the radius rho and the m omega squared, where omega is the angular rotation rate. And you get the force acting on a particle at the edge, which is effectively counteracting gravity. I know that centrifugal force isn't a real force, it's actually the centripetal force, etc. But for the purposes of this calculation, this is the easy way to treat it. And then you can work out that fights against gravity and reduces the overall temperature. And von Zeipel's theorem shows us that the effective temperature is proportional to the fourth root of the effective gravity. And of course, that flows from the Stefan Boltzmann law as well. So Altair is also a little bit variable, only tiny variations of a few thousandths of a magnitude, but with regular periods of under 2 hours, it is changing backwards and forwards, and that makes it an example of a delta Scuti variable. So what about its origins and its age? Well, early estimates were that it was 1 billion years old, but you can see it on the middle of the Hertzsprung-Russell diagram there between Sirius and Procyon. And in that position, you can do some maths and say, well, with 1.86 solar masses and 11 times the power output, a simple estimate tells you if you got 1.86 times the fuel and you burn it 11 times faster, you're going to run out in 750 million years. So being a billion years old is a bit optimistic. And indeed, most recently, estimates have worked out at under 100 million years, just 88 million years. So only 2% as old as the sun, which makes it very, very young indeed. As far as we know, we can't find any planets around it at this stage. And with that sub 100 million year age, perhaps the planets that it may or may not be in possession of are still small and are still growing. We don't know, but one way or another, it does seem like there hasn't been very long for planets to grow, to cool down, to form rocky surfaces and acquire oceans and do all the things that you need to do to trigger the evolution of life. And so, despite that, the mention in sci-fi, in Star Trek and elsewhere, is pretty common, perhaps because it's near to the sun, and perhaps because actually the estimates were that it was much older, up to 1 billion years, when those sci-fi stories were being written. And the new news is that it's just way too young for that. But I do remember Altair being the star around which the hypothetical planet Altair 4 orbited in The Forbidden Planet. So one of my favorite sci-fi movies of all time, with Dr. Morbius and Robbie the Robot and the power of the ancient civilization called the Krell. Absolutely wonderful sci-fi movie, and if it's on again, I'm pretty sure I'm going to watch it just for the fun of it. And well, wouldn't it be interesting if there was a planet Altair 4 in the end? We just haven't discovered any yet, perhaps because of that axial tilt. And I'll just leave you with a shot from the Forbidden Planet there, where I think the quote is, "This spaceship arranges its own eclipses." So a hypothetical planet passing in front of and blocking the light from Altair. I hope you've enjoyed that one, and we'll be back with more trips once around other objects later on.